Hi, everyone. Today we're starting chapter 11 talking about rolling. Okay, so we'll start talking about this image here. Okay, we can see here that one light source at the center of a rolling cylinder and another one on the rim of the cylinder show different paths that these objects take if they're rolling, right? The center moves in a straight line. That's your center of mass line, that green light there. And then the path on the rim moves in a path called a cycloid. Okay, cycloid is that specific path that's made when a round object rotates, or I guess rolls, on a flat surface. Okay, so first we're going to talk about what do these green and red lines have in common. So first, let's talk about the green line. Okay, the green line is the velocity at the center of mass. Okay, and that is if an object were rolling or just translating, right? If it's rolling, the center of mass moves evenly. If it's just being pushed, the center of mass just moves evenly, right? So that's rolling and transverse. I shouldn't write over those words. Let's see, rolling and transverse. Now for the red, right? That is the velocity on the edge. We'll call that VR. Okay, that is the velocity at the end of the radius, and that is only for rolling, right? That is not the same velocity if you were just transversing, right? Then that top would just continue to move about. Now we can also say that, well, yeah, let's not go into that. Okay, so red lines and green lines, okay, they both show the velocity of the object. It's just the velocity at different points on the object. Now, how can we describe the cycloid or the path of the red line mathematically? So if we were to describe that path, we could say that f of x is the absolute value of sine x. Okay. So if you took the absolute value of a sine graph, you would get that graph, right? You would see it hopping around instead of having the full mountains and valleys, right? The full sinusoidal curve that we're used to. Here you just have bunny hopping on its graph, right? So that is a sinusoidal graph. It's just the absolute value of sine. Okay, now what speeds can the edge have? So let's look at this demonstration or this image down here. Okay, here we have pure rotation. That means that it's not moving, it's just rotating in place. Okay, don't imagine that it's on a surface. Imagine that it is just rotating in space with no surface touching it. You have the edges, okay, they are rotating with V equals R omega. We'll go over that R omega in a minute. And then that center of mass goes nowhere, right? Because it's just rotating, right? It's not rolling, it's just rotating. So that's what happens with rotation. Now for translation, this is if the ball were just being pushed, right? Which is what we've done for almost all of our physics up to this point. We just assume things are being pushed and they're sliding across some frictionless surface, right? So let's say that that's what's happening here. This ball is just sliding across a frictionless surface. Here you've got the velocity on the top and the bottom, okay, where you've got contact at point P. All of those are moving at the same velocity, including the center of mass. All of it moves at the same velocity, and that is the velocity cm. Okay, you can see that is repeated in 3 different spots there. They all travel at the same velocity as the center of mass. Now last, we've got a combination of rotation and translation. Okay, this shows rolling, right? So if we combine those two concepts, right, in rotation, okay, your center of mass is not moving. But in translation, your center of mass has a velocity. So if we add those together, you've got the velocity cm, right? The center of mass will move with a given velocity as it rolls, just as if it were being translated meaning pushed, right? Now, if we were to look at the edges, this is going to be a little bit different. Now, in the edge up here, you've got r omega as it's rotating, and then the velocity cm as it's translating. So if we add those together over here, you can see that you've got the velocity of the center of mass plus r omega, and r omega is the velocity at the center of mass. So then you have 2 times the center of mass on the top of a rolling object, not rotating, rolling object. And now here's the even more confusing part. You've got v equals omega r, which we said over here on the top. That is the same as v center mass. And then you've got v center mass here, but they're opposing each other, meaning that in rotation, in rolling, that point technically doesn't move because it's the pivot. As an object as it rolls, you can kind of imagine that it's pivoting on its bottom, okay? But that pivot point moves every second, right? Every moment, that pivot point moves as it pivots, but that pivot point at any given time has no velocity. So those are the edges, the speeds of the edge, not the edges of the speed. Those are the speeds that the edge can have in a rolling object. So that's just kind of our introduction. Let's keep moving. So what is pure rolling? Okay, so pure rolling requires the object to roll without what? Well, that requires the object to roll without slipping. Okay, it cannot slip. It has to grip the surface perfectly. If there's any kind of slipping, if it starts skidding of any kind, then it's not pure rolling. So number 2 says, what kind of force is required to prevent that slipping? That requires friction. But this friction is not going to play like we usually think it does, right? Friction usually opposes our motion, but here friction is necessary for our motion. Okay? So if we avoid slipping, what is the relationship between VCM and omega if they are both constants? So we have this established image over here, right? As an object rolls this distance s, okay, you can see that line is on the circumference of the circle, and then it's actually given to you on the surface as well, right? So it rolls that arc length or distance s. That distance s is r theta, right? So that means that theta is s divided by r, right? It is s divided by the radius. Now, if we know that omega, omega is theta divided by time, right? That's just a fundamental rotational mechanics rule. The change in angle divided by time is your angular speed. Now we also know that velocity is s divided by t, right? However much of an arc length has moved, right? In that turn divided by time, that's your velocity. So we can combine all of these to say that v equals, if you've got s over t, you can say that s is r theta over t, right? And then omega is theta over t. So then you have r theta equals velocity, okay? But that r omega, not r theta. Velocity is r omega. But that r is different, right? We have used the equation v equals r omega. This VCM equals r omega, which you think that's ridiculous that we have a different equation for that, right? That we're going to say that those two are different, but they are. So here, this little r varies, right? R varies because the velocity in that equation is trying to find the velocity at a different point along the radius. But the velocity at the center of mass does not want to vary, right? We're not looking at the velocity along the radius. We're looking at the velocity at the center of mass. So here, the r is constant, this is just the radius of the object. We're not looking at what is a given position, right? Because the little r is just a position. But capital R, that is the radius of the object that we are talking about. And omega is the angular speed of the object we are talking about. Omega doesn't vary with radius, right? And that R, the capital R radius that we're using here, is not going to vary. It's going to be a set constant for your shape. So these are technically two different equations because those R's have different meanings. So that is our relationship between the velocity at the center of mass and angular speed. Now, let's talk about torque. Okay, we're going to have a torque analysis of rolling down a hill. So first, let's draw a free body diagram for a rolling ball down a hill. So we have hill, we have ball, right? So starting from the center of mass, you have mg, right? mg. Then you have your normal force coming off. That is perpendicular to the surface, right? So that is your normal force. Then you have your friction, okay, just like usual. Now, that's what we're going to say is our free body diagram for a rolling ball down a hill. Now, which forces are actually creating the torque to roll down the hill? Now, this is where this is going to get confusing because rolling is going to treat that friction differently. Okay, so if we draw our triangle like we usually do for gravity, right, and we've got this angle theta, we see that mg is a driving force down the hill and friction is supposedly opposing that force. But let's talk about that. Gravity causes the ball to slide down the hill. But if there's friction, the ball's not going to slide. If we say that this is static friction, now we say that that ball can't slide because it's not going to reach kinetic friction. It's only going to use static friction. So that means that this ball, I'm going to draw a bigger version of this. Give me a better incline there. Okay. So I'm going to say that if this is our center of mass, right, and we've got radius r, as gravity pulls on the center of mass, the gravity is pulling everywhere on the object, right? So gravity will pull on this part of the object here. It's going to pull the edge of the ball and it's going to cause it to roll downhill, right? That's what's going to cause this to roll because here we have static friction. So gravity causes the ball to fall downward, down the hill. But even though friction is there, we're not going to expect that friction to actually resist the rolling motion like we usually do, right? We usually assume that friction is resisting our slide or resisting our motion at all. Here, friction is actually allowing the roll to happen. It's necessary. So the friction is not going to prevent the torque from taking place, right? It's also not going to contribute to the torque. We are actually going to completely ignore the friction here because we're saying that this is pure rolling. Remember we talked about pure rolling before, right? Where did we talk about that? Pure rolling, okay? It can't slip and friction is necessary. So here the friction isn't going to prevent us from moving and it's not going to contribute or add more torque. It's just going to simply allow the torque to cause a roll instead of a rotation. Okay? So, and it's also going to prevent pure sliding. Okay? So, which force creates the torque to roll? We are only going to consider gravity. Now, it then asks us to calculate the acceleration. So we're going to use torque to do that. So let's go down here below. Okay, so we will use the equation torque equals I alpha because our goal is acceleration. Now it said acceleration, that we're going to assume that's linear, not angular acceleration. So if our torque, okay, our force is mg, and our, that is mg sine theta, right? If we look over here, the part that's actually contributing is this guy right here. So that is mg sine theta. Now, the radius, right? You've got force times radius. Well, we're just going to say that is radius r. So mg sine theta r equals moment of inertia times alpha. Now, what is our moment of inertia here? Well, we've got a sphere, right? So if this were the prefab, right? The prefab for a moment of inertia rotating about its center of mass is 2/5 mr squared. But this isn't rotating about its center of mass. Where is it rotating about? So remember, we talked about when rolling is taking place, right? When rolling takes place, let me get all this out of the way. When rolling takes place, it is pivoting about point P. So when we talk about the moment of inertia, we're going to have to use the parallel axis theorem. The parallel axis theorem is going to say, I lost my word, there it is. Parallel axis theorem, okay, says that a non-center of mass moment of inertia is the moment of inertia at the center of mass plus md squared. Well, the distance this is off the center of mass is the radius, right? It is just one radius down from the center of mass. So here you would have 2/5 mr squared plus mr squared. That would give you 7/5 mr squared. Okay. So now we're going to move that over here. We now have mg sine theta r equals 7/5 mr squared alpha. Okay. Now, if we cancel the masses, and we're going to solve for alpha, right? If we divide that r squared over, we have g sine theta. That r is going to cancel with one of those r's. So then you're dividing by 7/5, which is the same as multiplying by 5/7 times the radius, and that equals alpha, right? Now, if alpha equals a over r, right? Yeah, alpha equals a over r, so that means that we're going to divide again by a radius. So that means that you get 5/7 g sine theta equals your acceleration. Okay. So what we did is we multiplied this r here to the other side and canceled it with the radius that was in the denominator to solve for our linear acceleration. So we get 5/7 g sine theta. Okay, that is the acceleration, part 3. Okay, now evaluate when you roll down a 90-degree incline. It's 90-degree plane. It's weird. So if we look at that, okay, we've got our acceleration is 5/7 g sine theta, but here theta is 90 degrees. That means that sine theta would be 1, right? So acceleration is 5/7 g. Well, that's weird, right? So if you roll down a straight incline, right, you're at 90 degrees, but you are assuming pure rolling, right, which means that your sphere, right? Yeah, your sphere is in constant contact with the plane as it goes down the 90-degree plane. So because the gravity has to roll the ball, right, that actually diminishes the acceleration, because it's not just pulling on the center of mass and just with no resistance, right? It's actually having to roll the ball. And since it has to roll the ball or roll the sphere, that actually decreases the acceleration due to gravity, right? So instead of g, you get 5/7 g if you have to roll down, the 90-degree plane. Even though it's straight down, the fact that you are rolling means that you're going to accelerate slower than if you were free falling, which is bizarre, but really cool. Now, what matters in rolling? Your mass, your radius, or your moment of inertia. So if we look over here, okay, the mass and the radius all got canceled, right? We've got mass here, radius here, mass here, radius here, radius there, radius there. They all get canceled away. But what is really important here is this, the 7/5, that fraction. That stuck around the entire time, and that is actually the thing that mattered the most once we got down to it. So your moment of inertia is what's going to be the most important here. When we had this moment of inertia, that 7/5 already determined the ratio that was going to take place later, right? The mass and the radius, it doesn't matter what the mass of the sphere is, what the radius of the sphere is, but that ratio in the moment of inertia is going to affect the entire thing. Right? So that's our torque analysis of rolling down a hill or rolling down a 90-degree incline. Now, let's talk about an energy analysis of rolling down a hill. So here what we want to do is derive the equation for pure rolling velocity center of mass using a COE. So let's use a COE. Okay. Our COE, we're going to say that it starts with initial gravitational potential, right? It's starting at rest, so there is no kinetic energy to deal with. Then we will say that the final gravitational potential energy, we'll call that the ZPL, that's our zero potential level. But that means that it now has translational kinetic energy and rotational kinetic energy for rolling, right? So we already have these equations. We're not using any new equations. But now what we're going to do is we're going to talk about this rolling down a hill. We're going to combine these kinetic energies, or I guess use them in the same equation. So we have mgh equals 1/2 mv center of mass squared plus 1/2 I omega squared. Okay. So we need to get that omega in terms of VCM, right? Yeah, that's what we're shooting for. We're shooting for velocity of the center of mass. So omega, right, is the velocity of the center of mass divided by the radius of the object, right? Remember we talked about how that capital R is different from the lowercase r. So let's put that in. We also know the moment of inertia of this object, right? The moment of inertia, right? So here we don't actually care about the parallel axis theorem. We're just talking about the kinetic energy of the object. So here we're not actually taking into consideration that this is pivoting about the bottom, right? Because the kinetic energy is only worried about what's happening at the center of mass. Okay, so we're actually not going to consider this as 7/5 like last time. This will be 2/5 mr squared, and it'll all work out, I promise. So if we plug these in, we have mgh equals 1/2 mv center mass squared plus 1/2 times 2/5 mr squared. And our omega squared becomes v center mass squared over r squared. Okay. Right off the bat, r squared and r squared are out. M, and m, you can divide those through. So let's see what we're left with. We are left with gh equals, we'll factor out that 1/2 and the v squared. So you've got 1/2 v center mass squared times let's leave that in there. So we've got something. I don't want that to just be a 1. So then that is 1/2 plus, let's see, these 2's are going to cancel. So then you just have 1/5. So then you have 1/5 M's are gone, R's are gone. Wow, that is it. That's all we have left. So that leaves us with 5/10, 2/10, so 7/10. So then you have 7/10 of the velocity squared. So if we solve for that, you then get 10gh. Sorry, my dog is freaking out. All right, so if we solve for velocity, we'll divide that fraction over, multiply by the reciprocal, so you get 10/7 gh equals VCM squared. Let's not even square that. Let's just take the square root. So the velocity of the center of mass is the square root of 10/7 gh. And that is from the COE, from conservation of energy. Now remember, this was a little screwy, right? You'd think that the kinetic energy would care, right? But the kinetic energy doesn't care about the parallel axis theorem. It just cares about rotation, right? This is not rolling kinetic energy. This is rotational kinetic energy. If an object is rotating, it has a set amount of energy. Now, it doesn't matter if it's rotating about something else, right? It just cares about, is it rotating? And here it is, it's rotating, right? So you just have 1/2 I omega squared. All right, so that is our equation for pure rolling. Now, where is friction in this equation? So friction is not there, right? Usually we have some kind of work of friction off to the side, right? We'll have plus work friction, but that's not there, excuse me. So that's because it's rolling at point P, not at the center of mass, which is confusing, right? But we're not going to take into account this friction because the friction is not going to take away energy, right? So when you have friction in a conservation of energy problem, that means that the friction is taking away some of your energy, right? It's basically a non-conservative force that is taking away energy from an otherwise conservative system. But here, friction isn't doing that, right? Friction doesn't take away any of your mechanical energy. So we don't even consider it, right? That's why we don't see friction in this equation. Now, theoretically, is mechanical energy loss due to what's called rolling friction? And then my students wanted a reference to this. So I gave them, there's a Wikipedia article on rolling resistance, same thing. So they wanted to see that Wikipedia article, or in the textbook that we use, it's I think the 9th edition of Survey. That's what we're using for now. We're getting new textbooks soon. But it's page 318 in that textbook. But the idea of rolling friction, right? The idea of rolling friction is that as an object rolls over a surface, the object gets deformed ever so slightly as it's rolling, and even the surface ever so slightly gets deformed. And that will draw mechanical energy out of the system or out of the scenario. And also if there's friction inside the axle, right? If the axle doesn't perfectly rotate smoothly, if there's any kind of friction within the axle, that can also cause loss of mechanical energy, right? So rolling friction is the deformation of the object or deformation of the surface, transferring some mechanical energy into internal energy, right? Which isn't something that we really go over in this class, but it's there. Now, theoretically, yes, there's mechanical energy loss due to rolling friction, but we're not going to consider that in this problem. Now, let's talk about the linear acceleration from our previous problem, that energy analysis, right? So for a solid sphere, find the linear acceleration using kinematics and your new VCM equation. Okay, so our VCM, I'll rewrite that, is the square root of 10/7 GH, right? Now, if we were going to find acceleration, let's use V final squared equals V naught squared plus 2a delta x, right? We don't need time here, and we do have an x in the problem. Now, interestingly enough, kinematics, all right, that doesn't care about height. So let's look at that triangle, right? If height is here, x is our hypotenuse. We've got opposite and hypotenuse, that would be sine. So sine theta is opposite over hypotenuse. So h would be x sine theta, right? So we can substitute that in, right? Now, we also, okay, we're starting at rest. So that's gone. So let's substitute this in. Our v is in a square root, so v squared, we're going to get rid of that square root. So here we have 10/7 g x sine theta equals 2ax, right? So if we're solving for x, we're going to divide by 2 or multiply by the reciprocal, right? So we would then get 10/14. I know that reduces. G, the x's are going to go away. So you have g 10/14 g sine theta, which is 5/7 g sine theta equals the linear acceleration of the object, right? Now, how does this compare to the answer we got using torque? That should look really familiar because that's the exact same answer we got last time, right? But remember, torque actually took into account that pivot point. It actually took into account that axis of rotation because it used the parallel axis theorem. But using that kinetic energy, you didn't use the parallel axis theorem, but we were still able to get the right answer, right? We got the exact same answer. So which is better, torque or energy? We got the same answer, right? It really is going to depend on what information you're given for the problem, right? Also on torque, we were able to go directly to acceleration, right? With energy, we found the velocity first, and then we had to use kinematics to get acceleration. So depending on what you are asked to do, torque can go directly to acceleration, right? Torque equals I alpha, and acceleration is a really easy conversion. But if it asks you to do velocity in the meantime, right? If it says, take this scenario, find the velocity and the acceleration, if that's what it asks you, do energy, right? You will find the velocity on your way to get the acceleration. So you're able to kill two birds with one stone, right? Now, are you sure you buy that acceleration is less than g at 90 degrees? Well, I'm going to leave you to ponder that one. And that's the end of our video as well. So next, we will continue on with a second part of rolling. We're going to do a rolling part 1 and a rolling part 2 before we begin angular momentum.